Yeah, so I'm gonna talk about some application of shape analysis. So I'm not really contributing for this talk on the shape analysis, but just using it. And I will spend some time to present you how I can go from some stochastic processes and to some representation on the Lie group, and then after use shape analysis to say something about that. So the main context is about radar. We're interested here by the echoes produced by some pulses sending on the radar. And we are actually sampling those echoes to have a time series. And we have some information on this time series given by the spectral density associated with it. The assumption is that those processes, those echoes, are periodically correlated. That means that the correlation matrix is periodic. Okay, it's quite the thing. This is due to the modulation of the echoes actually, and the pulses sending by the radar. So the aim of the application is to detect if we have a target in the field of the radar or not. The idea that we use is that we're actually trying to have a better representation for the spectral density of the echoes, and then to have some signature associated with and try to compare those signatures along with time. So this work was a part of the work of one of my PhD students, Marie Dugas, so I invite you to read this PhD documents if you want to have some information about what I'm gonna talk. This is also this work could also be seen as an evolution and a continuity of the work of Alice Lebrigand. I mentioned that at least for the context of the radar, because we use next some different shape analysis approaches, but you can also read some useful information inside the PhD document of Alice. And the next part is that we use some results of Celedoni and her colleagues for the shape analysis. Okay. So the motivation and just the contribution is about what I put on the last bullet, is that instead of using the sequence of partial correlation coefficients associated with the spectral density of our process, as it was done by Alice on her PhD, we go a bit further on the representation of this spectral density and spectral measure by embedding it on the Lie group using the dilation theory. So I'm just present you the basics of the dilations. This is a theoretical approach, mainly of some Russian people actually. That's not really known in France, but I'm gonna try to give you the concept and the basics of this dilation theory. I will start the talk and this by just introducing to you what we call the shift operator. We can model our time series actually, which is materialized here by the sequence xt. We can represent this time series of this sequence in a Hilbert space, which is found by all the time sample of your time series. So, we can use next what we call the shift operator, which is the operator, the unitary operator, which is ut here. And in this representation on a Hilbert space, we can know that all the sequences are all known thanks to this unitary operator ut. That's quite easy to understand, but all the spectral components, all the radon are contained inside this operator. Actually, you can find it many times in the literature with different names. Some people have named it, I think, some the Markov operator, something like this, so you can find some results about the Markov operator. But this has the same context and the same ideas, that we can go from one sequence to the other one just by using and applying this unitary operator. Actually, how can we reach the dilation theory? I will present next here a representation for the covariance matrix of your signal. I propose here the approach given by Alexander Veron, who use the concept of representation, and just by saying that the covariance matrix could be expressed by those expressions where we have the characters on a specific group, and the spectral measure f here. We recognize here when the group is the real, the characters are the classical characters, which are the exponential functions, and then we have the classical Fourier transform. That means that basically we have the covariance matrix, which could be just the Fourier transform of the spectral density. That means that. The way is that we can here now use the shift operator in this expression to obtain just an expression which is equivalent here, for which the covariance function here could be expressed in the group by some other spectral measure, which is not associated directly to the measure of your process, but which is associated to the unitary operator. That means that you have shifted the problem to the unit operator to another operator, which is a bigger one, actually. This is explained here. We have actually the spectral measure f, which is expressed by E, another spectral measure, which is the spectral measure of the unitary operator and the shift operator here. What does it mean actually? And basically, that means that we have a spectral dilation of our spectral measure associated with our process, which is E here, and our spectral measure of interest, F, is actually contained in an upper left corner of this bigger spectral measure. That means that here we've got something of interest which is included in a bigger space, in a bigger operator. Why is useful? We will see just later on the presentation in a few slides. But here we have the basics of the dilations, and that means that we can connect what the previous results with what we call the Neymark dilation, which says that for any sequence of operators, which was positive definite, we have an expression with a unitary operator, an isometry actually here, which is called U, and that means exactly that each correlation coefficient could be expressed and dilated thanks to a bigger operator, which is U. Here we use U, we project and reduce its dimension, and we catch the correlation coefficients of the correlation function. So, if we talk in a scalar manner, that means that if we have just one coefficient, this coefficient is included in the upper left corner of a bigger matrix. And this matrix has a big sense, we will see later, because inside all the spectral components, all the randomness of your process is contained inside this matrix. So this matrix has a big sense, and we will see that his structure is very useful for shape analysis. What I talk so far is for stationary sequences. What about when we are in the non-stationary case? In the non-stationary case, actually, we have a spectral component which evolved during time. That means that we will not have only one operator at a time, but many operators for each time. of your sequences. So that's explained here. Your sequences xt is no more explained by only one operator, but the product of many operators. This is the Kolmogorov Decomposition, which is stated in Konstantinescu book, which says basically exactly the same. Instead of using one operator, we have many ones. So for a positive definite kernel, then we multiply, we have the product of those operators, we project and reduce the dimensions, and we catch the coefficients, the correlation coefficients associated with your process, and non-stationary process. The good point is that for the general non-stationary case, that would be difficult to catch all these operators during the time, but we will use here the assumption of periodically correlated. That means that we have many tools to catch those operators, and we will see that actually we have a finite set of operators due to the periodicity of your process and the periodicity of your statistics. And that means that we have a finite set of those operators, which actually are periodic as well. So, how can we reach and how can we obtain those operators, those U operators? We have here, we can reach them with different manner in several ways. I'm just gonna present you one of these ways in two parts. The main point and the first one is just to recall that we have a one-to-one correspondence between the correlation matrix of your process and the partial correlation coefficients that we call the parcours. If you need to have more details about that, we have many books, and once again you can read the PhD thesis of Alice Lebrigand or Maë d'Auguste, and you have all the information about this correspondence. But this is due to Berg and past works, actually pretty old work, but and actually you can find all those coefficients with the Geronimo coefficients, Verbludsky coefficients, all the topic about the decomposition or your measure on the unit circle, what we call orthogonal polynomial on the unit circle, OPUC. Okay, so you can find everything which explains to you on the correspondence between the correlation matrix and the partial correlation, the parcours. So Konstantinescu, in his work, associates another matrix to your correlation matrix, which is the matrix gamma, which has this form. This is for the general non-stationary case. If you are in the stationary case, then this matrix is templates. It's band templates. No, that means that you just copy paste all the first row on your matrix. So this is the first point to use. Okay, we've got a correlation matrix and some other matrix, which is the matrix gamma with some partial correlation coefficients inside. The second point is the way that due to the consideration of your correlation coefficients, all your coefficients are of modulus less than 1. So they are contained inside a unit disk. And that's useful because we fall down a new theorem proposed by Almos, which states that we have an expression for the dilation for those coefficients. That means that if you have a coefficient, a correlation coefficient gamma, then we have an explicit expression for the dilation associated with those contractions. This is written just at the bottom here. Your operator U is equal to this matrix, which actually is basically a rotation matrix. That means that the dilation of a contraction, the dilation operator, the dilation matrix associated with one coefficient in the scalar case is only a rotation matrix. And we just have to compose with those different rotations associated with the different partial correlation coefficients to build the matrix. This is written here, our expected unitary operator, UI, here, is actually the composition of different rotation matrices. See, and those matrices are written here in the global case. So we've got an invariance along the diagonal of your matrix, and you've got the different rotations inside here. This is the given rotation matrix. Okay, so once you compose with this, you obtain this matrix, which is the expected matrix. This is an upper Essenberg matrix. You can find this matrix in many fields, actually, in physics, with the todalities, with many fields, actually, even in the decomposition of your measure in the theoretical way. You've got this matrix. This is also, which is very important to me, this is also an expression for the evolution operator. For a signal, if you want to know how your signal evolved, which is related to the physics and quantum expressions, you will find this matrix as well. So this matrix is very a key point actually in physics, because this matrix, try to describe some physical elements and the relation between those elements. So this is a matrix which is very important. Okay, so at this step we have all the information for building our dilation matrix, and the next step is just to have a representation of those matrices in a complex case. So for the case of the special unitary groups, we can find some different parameterizations to have a representation, just to see what happened about the curves. And I found this representation for the special unitary group of Bouleux 4, which uses the Lie algebra of your point inside this group. Once you parameterize with three elements, and you can visualize the curve associated with your operator. Okay. Some examples now. I was talking at the beginning about the radar application, so I will use some data given by Frederic Barbaresco on Doppler radar. And I just first propose you to be convinced that the assumption of periodically correlated assumption is not violated for this application, because here I propose you the square current statistics associated with some echoes at the time. First on left, this is when there's no target in the field of the radar, and the right, this is when there is a target. What we can see here is the frequency to frequency representation of the covariance statistics. That means that when your process is stationary, you've got the black line here, only the black line, and when you have a non-stationary conditions, then your spectral molecule spread off inside this square, and that we can see here. The important point is that with the assumption of periodically correlated functions, we have some parallel lines to the main diagonal one. Here we've got that for no target and for the target one, when there is the presence of the target. The point is that we have many other periodicity inside our acquisition, so that means that could be difficult next. Okay, so the representation, what we obtain at the end is that actually what could be strange and weird is that for all the representation, the module of the representation is quite the same for all of the time instants. So actually we have only two parameters for the representation. That's why I'm just representing it inside a square and not a sphere. This is actually just a zoom in a small portion of your ball. And then we have here no target on the left and target detected on the right. We have some, okay, different curves and different trajectory for our process. And then we can now do some stuff to classify or to do some distances. Okay. Okay, we will see and we'll talk about this next if you want. So just I want to make a break before using the shape analysis now, just to recall you, thank you. Just to recall you that we started from a correlation coefficients, a correlation matrix of a time series, then we put and we embed this time series inside the Lie group, which is here in the complex case the special unitary group, and we use those contractions to build the dilation matrices. Since we have many different matrices, dilation matrices associated with each time, we have a path on this special unitary group, and then we can perform everything. We can discriminate the shapes and then calculate and compute the distances. We can have some topological information given by the different points. We can even do some clustering. Okay, so here and for the third time of this session, I will present and use the shape analysis. So we have the basics of the shape analysis, and we have used the results, as I said at the beginning of Celedoni and her colleagues, for doing and computing the distance in homogeneous spaces. So since I don't have the time to go, and since all of you knows this way to compute the distances, I use for that case the dynamic programming to solve the problem, and this is the end. Okay, we have the different distances. Actually here we have a distances of 80, and we have many different distances between the time instance of the echoes. Okay, thank you very much for your attention.